Give it a shot. Be bold. Make mistakes. Get messy. I'm not sure whether you want to speak and just want to let someone else speak, or whether you haven't made up your mind yet.
Bit of both.
Bit of a, okay. That was not as grand an entrance as I was hoping.
Oh, I thought you were gonna talk, sorry.
Just waiting for someone to tell me units. Go ahead.
Isn't it just number of people per pre-built civilization?
Yeah, okay. So this is people, we'll just label it as P for people. Per pre-post-human civilization. All right. So what it would be, if I multiply this times this times this, what will my units be? So let's get rid of that stuff. Give myself some room here. So if we post-human civilizations divided by number of civilizations times number of ancestor simulations per post-human civilization times the number of people for a pre-post-human civilization, what would you end up with? All right, you're either shy or you don't know that you know this. If I did 3/4 times 1/3, what would you get? All right, the silence here is troubling.
3/12.
1/4. All right, and you could do 3/12, that's fine, but how could you have done this a little bit faster instead of going 3/12 first?
Cancel out the 3's.
Okay, so if I have the same thing, if I'm multiplying, I have the same thing on top and bottom, I can get rid of it. So, up here, can I get rid of anything? Not the pre-post, but just the post. Those would cancel out. So I'm left with people, ancestor simulations per civilization, pre-post-human civilization. It's an odd unit, granted. So I get people, so my units are people, ancestor simulations are PN sims times C PPHCs. Oh, sorry, that's just the top here. So now, well, that's the same thing. That would have the same units. Are the units of H bar the same as the units of this?
Partially.
Yeah, partially doesn't count. So he's adding some, this is some number with units like this to some number here with different units. And there's not a conversion factor. It'd be like, what is 4 seconds plus 3 meters? Just by, this is known as dimensional analysis. Just by dimensional analysis, it's very clear this equation's wrong. Now, there's also a whole lot of assumptions he made, which I think are complete crap too, but. Now, he did, 10 years later, come out with a correction for this. With an opening line along the lines of, nobody seemed to notice that there was a problem with the equation. So one lesson from this is, if this group is a very quiet group, Yeah, there's gonna be a whole lot of silence. I have found that classes where people ask a lot of questions tend to do better. And two, units are critically important. We will be dealing primarily with meters, seconds, kilograms. Those are three of the basic units. This is, actually, I'm gonna put it in a slightly different order. This is known as the MKS system, which is also this international standard. I think that's spelled right. It's supposed to be the French writing of international standard. So otherwise known as the SI system. So the measurements you were doing in lab yesterday where you had centimeters, that is not part of the international standard. It is a standard unit, it's just not part of international standard. So that's one reason to convert things into meters. You did grams into kilograms, presumably. And we tend to stick with seconds. So quantities such as speed, what would be the international standard for speed?
Meters per second.
Yep. International unit of time,
Seconds.
international unit of position,
Meter.
I think somebody just said meter. If you watch the orientation video, you know that my hearing is not great. Just be loud and proud. So when I wrote up those equations over there, one of the equations I wrote up was that delta S is equal to VIT plus 1/2 AT squared. A, change in velocity over change in time. This is actually average. So if we're looking at units here, units of change in velocity, well, velocity and speed have the same units. So that would be meter per second divided by time, which is seconds. So my units of acceleration, the standard units of acceleration would be meters per second divided by seconds, which is a meter per second times 1/seconds, which is a meter per second squared. So is this equation dimensionally balanced? Well, by units of position are meters. So what would be the units of change in position?
Meters.
Yeah. So I have meters is equal to velocity, which is a meter per second, times seconds, plus 1/2, well, that has no units, plus A, meters per second squared, times seconds squared. Is that dimensionally balanced? I see two people shaking their head yes, or nodding, I guess it's called. Can we get a third? All right, we have at least 3, 4, 5, we got a groundswell, 6. This column over here seems rather, there we go, got at least one from over here. Now, so, as has been noted elsewhere, I do expect units in the answer if there are units in the question. I guess the exception is, if you end up with units, say, meters per meter, you don't have to write meters per meter, you can just get rid of those. Actually, what unit actually doesn't matter if you write it or not? It's a unitless unit. many of you have had trig? 1, 2. And a half.
What was the question?
How many of you have had trig? So I think we're up to 6 now. In trig, there's an equation. Actually, it shows a number of places. S equals r theta. Anyone happen to know what S, R, and theta stand for?
Arc length equals radius of the times the angle.
Yeah, all right. So if this is arc length, it's a length, so units of meters. Radius, that's a distance, it's meters, times whatever the units of theta are. So the units of theta would be meters over meters, otherwise known as
One?
that is acceptable. There's actually a non-one answer. Radian. Abbreviated as RAD. So there are times in which you would write radians, although radians is always optional whether you write it or not. All right, questions before we venture into the hallway for a little bit? You feel like you just came in partway?
Yeah, I did.
All right, let's venture into the hallway. I need 3 volunteers. Oops, sorry. All right, so why was Miranda able to touch it relatively easily to the ground? What about it? It doesn't stretch. I mean, it's the material doesn't stretch very much. So
She able to put more force, like, in one area, or more than what they could do, separate the rope. It's hard to explain.
it depends on what you mean by that. As in, she just
Like,
she was just so incredibly powerful. She had more power in her finger than the other two did completely. Is that what you're going for?
I guess.
Oh, all right.
Her force was more compacted to one area, and the other force was spread out across the whole rope.
No,
I mean, it's
the
probably.
way the rope works, especially if it's ideal, the force that they were exerting was the same pretty much throughout the entire one. And Brandon, you were saying something to the brewer?
So, I mean, it was probably easier for me to push down than it is for them to pull outwards, because you have a tendency to fall forwards, maybe.
You have now seen the ballpark.
So it's a combination of the two. It's when we're pulling away from each other, it's easier to push down because you're not directly going against our force, but specifically doing it in one spot, it kind of just overwhelms the force that we're exerting in one specific area.
All right, so before she touched it, think about how much force you were exerting on it before she touched it. And then once she touched it, did it increase significantly or just a little bit? Okay. Same experience or different? Okay. Where was most of your effort going?
Away, like pulling back.
Okay, yeah, and then with some of the hand gestures, but they were mainly fighting against each other. They were doing very little to stop Miranda. So, all 3 of them applied forces. The force that Evan and Brewer were exerting was roughly about the same magnitude. Not the same force, same magnitude though. But the key point here, the direction matters. So there are some quantities where direction matters and some quantities that don't. I mean, for example, the number of people in this classroom. Direction really doesn't make sense there. So that is a quantity that doesn't require direction. However, for force, direction does matter. And for those quantities where direction matters, these are known as vectors. For quantities where direction does not matter, what are they known as? Scalars, generally pronounced. Scalars is what you've been working with since kindergarten, or whenever you first started to count. An example of some scalar math: 1 plus 2 is equal to 3. That is scalar math. Vector math is a little bit more complicated. Because direction matters, in order to add them, I need to know what direction these things are going in. So vectors, so scalars, a mathematical construct with a magnitude and this is a mathematical construct with magnitude and direction. All right, so the math is a little bit different. So first off, how do I represent a vector? Well, I can represent a vector several different ways. One of the ways, if I have some vector A, well, I definitely don't want to write the word vector out too much because, well, frankly, mathematicians and physicists, I sometimes call them lazy, but my wife corrected me and she said they're efficient. We want to write what the fact that A is a vector efficiently, and so what I tend to do is I'll write the letter A and then put a vector symbol over it. That symbol on top is not telling me direction, it's just telling me there is a direction in some way. One of the videos I go through other ways that this can be expressed. I'll let you watch that. So I can also represent a vector more specifically that indicates a direction, and then the size of the arrow is proportional to the magnitude of the vector. So if I have two vectors in the same direction, if this represents 5 meters, this represents something under 5 meters if I'm drawing it to scale. Matter of fact, by the way I've drawn it, that looks like about 2.2 meters. If I really wanted to be precise, I'd pull out a ruler, measure the lengths, and get an actual proportion there. And there is a decimal point in there. So if I walk 5 meters east, and then I walk, let's go 7 meters north, how far have I walked?
12 meters.
Yeah. The distance I traveled is 12 meters. Where am I relative to where I started? How would you figure it out? Yeah. So I'm going to draw it out. I go 5 meters this way, so that's 5 meters, and then I go 7 meters this way. And so where am I relative to where I started? Well, this is where I started, and that's where I am relative to that. This has a magnitude, it has a direction. So Pythagorean theorem will get me half my answer. So I'm just gonna call this R for resultant. So R squared is equal to 7 squared plus 5 squared. The magnitude of my resultant is, oh, actually, going magnitude, I could just write plain old R equals the square root of 74. I got a thumbs up, all right. If the question was, how far am I from where I started? Then I would take 3 points off for this answer on a 10-point question. What's wrong with this as an answer?
Doesn't have a unit.
Yep, that's it. Square root of 74, 8.5-ish. Somebody have a calculator, they could.
$8.66.
8.66. Now, you might be thinking square root of 74 is a more precise answer, and this is rounded off, and yes, that's true. But all the base measurements that we're dealing with here, 5 meters, presumably that's rounded off and that's rounded off. Technically, one significant figure, so if I cared about significant figures, the answer would be 9 meters. But I don't care about significant figures here because it's not the first class. How do I find the direction?
Tangent of, or our tangent of 705.
Yep. All right, so if you are not familiar with SOHCAHTOA or you have not done right triangle trig, that chapter 1 review in math, the chapter 1 under coursework, I've got some review of